Hello everyone, thank you for coming. My name is Gonçalo Nogueira, and today I'll be presenting to you state-of-the-art FinFET technology, an industry designer's perspective, namely my perspective. So in this presentation, I'll be first giving an introduction to planar transistors, explain also why the need to develop and to go on to FinFET transistors. Then I'll present what FinFET transistors are, gonna explain how to design with them or give you some brief ideas. And after this I'm going to do a small pause, 5 minutes, just for to have a little rest, get some breath, and answer some of your questions. After that we'll advance on to the second half, where I'll be speaking about the advantages of FinFETs in comparison with planar bulk technology. Gonna after that speak about the challenges of working with FinFETs, and last but not least give you a brief idea of the potential future of solid-state circuits. So let's move on to transistors. So probably you all recognize this image over here. It's about Moore's law. Moore predicted many years ago that every 2 years the number of transistors in a chip would double. So where does this come from? It comes from the fact that it was theorized many years ago that scaling digital circuits would decrease the power and increase the speeds of these circuits. So people started noticing the potential in this scaling, and as such a market demand was created where you have faster, smaller and less power consuming circuits, and inevitably this led on to the need for transistor scaling research. So now on to the planar bulk CMOS. So this is the most commonly used transistor everywhere. It's the planar bulk CMOS. And ideally, as in digital applications, this is used as a switch. So what does this mean? Here you've got the drain, here you've got the source, and here you've got the gate. When the voltage at the gate is high, drain and source are supposed to be shorted. When the gate voltage is supposed to be low, these and these are supposed to be open circuits. So what are the issues with scaling? So for you to notice, the distance from ear to ear, it's the length, and here you've got the channel region. So one of the main scaling issues was leakage. Where does leakage come from? So imagine that you're starting to get these two closer together. What happens? So the gate here, when the transistor is shut off, this region here does not, there is not much current passing through here. So what happens is that you start having current flowing through the substrate. This is leakage. This is one of the main reasons why the planar was no longer a good choice for being used as a transistor. And also you have an effect called drain-induced barrier lowering. So as we approach drain and source, the drain, although here is depicted with it's depicted here as having no transition at all. It's not exactly like this. There's a transition from ear to ear. And as you approach this, and as you increase the drain voltage, the drain starts to protrude into the channel region, starts to enter, and it's going to change the threshold voltage. This has become so preeminent that also it's one of the main reasons to move onto another, a different structure for the transistor. Just to give you more or less an idea, here you've got the problem of leakage. So the dynamic power density that you see here is the power consumed by the circuit in operation that it's supposed to consumed in operation. And this static power density here is the power consumed by leakage. And as you start scaling down the transistor, the leakage starts growing and growing and catching up with the dynamic power density. This, of course, it's not acceptable. So let me start presenting you what were the ideas created to overcome these issues. One of the first technologies to appear was fully depleted silicon on insulator, FDSOI. So here you can see a cut of the section of the planar bulk transistor, and the way that the leakage was mitigated here, this insulator, this silicon oxide, it was deposited a thin layer of silicon oxides below this region. This way, you could overcome leakage. And also a second, the second option was the FinFET. So it started like this, the CMOS transistor, and it evolved onto this. So you brought everything up. This is not the best cut of the transistor, but the idea is that the gate becomes all around, gets all around the channel. So let me show you more into detail. Here you've got the structure of a tri-gate FinFET. Source and drain, this constitutes the fin, and then here you've got the gate. Silicon oxide, and here you've got the body, or the P substrates. So these views are front view, top view, and side view. But just one thing also, this thing that you see here on yellow, it's the it's also silicon oxide. It isolates the gate from the channel. So, although you're seeing this here, don't forget that this transistor is an NPN or PNP transistor. So, there's a channel inside. It's different. Now, how does a structure with multiple fins looks like? So, you just grab the fins and you stack them in parallel, like this. So as for layout, this is for people who enjoy layout and want to know a little bit more about layout with FinFET. In 3D, can you imagine it this way? You have a metal layer that connects here all the sources. You have a metal layer that connects here all the drains, and then here you have contacts onto the first layer of metal. I also have this slide for you to more or less get a feeling of how does it look like in 3D, how it look like on the inside. Now, onto transistor design. How do you calculate the width and the length of a transistor, or of a FinFET transistor? So, the length is given by the length of the channel. Now, does anyone here know how to calculate the width of the FinFET transistor? No? Okay, I'll tell you. See this here around? This is the effective width of the channel. So it's the perimeter. So it's given by the width of the fin plus 2 times the height of the fin. And designing with these transistors means that you can only define discrete values for the width. As per the length, there are some technologies that only have a single size transistor, single W, single L. You've got other technologies that can have multiple size intervals. So you can have, for instance, 20 nanometers, 40 nanometers, 60, 80, and then from there go from 100 to 150 nanometers. You can choose any value. So how do you increase the width of transistors? So you stack them in parallel. This is the way it looks like in a schematic version. You short the sources, short the drains, and short the gates. For you to imagine it better here in 3D, imagine that you grab all the fins and you bring them together. So this means that you have these as width of the transistor. That's 3 times the width. As per the length, you can increase the length by stacking transistors in series. You short the gate, define source and drain on one side, and this is more or less how it looks in 3D. You can also imagine, like I did before, that you grab all the gates and you push them together, then you have a free L transistor. You grab all the, you join all the yellow parts, and it becomes a free L transistor. So, so I would like to introduce you now a part of advanced nodes, which is inevitable, which are the short channel effects. So, like I told you before, you've got the drain-induced barrier lowering effect on the transistor, which causes the threshold voltage to vary. So, as you decrease after a certain length, this effect becomes more and more prominent. You decrease the after you decrease through more or less a critical length, the threshold voltage starts to decrease as well. The drain-induced barrier lowering effect is not only related to the length of the transistor; it's also related to the drain voltage, namely the drain to source voltage. And if you decrease the drain to, if you increase the drain to source voltage, the threshold voltage is going to decrease. This degrades the performance of the transistor significantly. Also, for most of you who haven't heard about this, there's also another effect called carrier velocity saturation. This was quite interesting the first time I found about this. So the idea is that usually you have this formula. This formula applies for all transistors, planar, FinFET, and the FDSOI, I believe. But you have this formula which is derived from the velocity of the carriers in the channel times the charge in the channel. But the truth is, as you scale down the transistor, as the dimensions become smaller and smaller, the electrical fields inside that channel become so intense that the carriers get saturation velocity. This means that they become the current becomes proportional to VGS minus the threshold voltage instead of quadratically. The first time I saw this on a model was really interesting. I wasn't expecting it. Now, why is this important? Let's talk about the analog design flow. So when you're designing a circuit, you define some specs. I want the circuit to work like this. You define a circuit. Okay, I'm going to set the transistor like this, like that. And you define, okay, this needs to have a certain GM, certain GDS. And for most, for people like me that just got out fresh off uni, my first idea is, okay, let's do end estimation. Let's grab this formula and use this formula to size my transistors, and then let me check with the simulations if the circuit works as I expected. But first of all, this new n varies with width, with length. This threshold voltage varies with width, length, with the VDS, and you can no longer rely on this formula to use to size your transistors. So my idea for you is to use GM over ID simulations. So you plot the GM over ID, you plot the transistors of the transistor parameters as a function of GM over ID. You define operating points for the transistor. You size them, and then you go and verify and check if everything is on point. Actually, when I was doing a circuit, I did a circuit for my company, and I used this method. The circuit had 20 to 30 nodes. After I sized everything, I went to check, and no node was off by more than 10 millivolts. That for me was incredible. almost didn't believe. So the idea here is to use this as a starting point. You do your design, and using the behavior of the transistors, you define the operating points, and then you bring all together, and you have it as a better starting point. So what is GM over ID methodology? It's a graphical methodology where you plot the transistor parameters, you see how does the technology behave, and you use that. You define values for the circuit specs, you plot transistor parameters versus GM over ID, you select operating points for each transistor, and you build the circuit. It seems very simple, I know. It can be a little complicated for people who have never done it before. So in saturation region, I want to explain you a little bit better for you what GM over ID consists on. So in saturation region, for VGS higher than the threshold voltage, you've got this formula for a fixed ID. So GM over ID is given by 2 dividing by VGS minus the threshold voltage. For those of you who haven't heard about it, this is usually called the overdrive voltage, and this is the ideal behavior. For those of you who also haven't heard about it or didn't think about it, the transistor is still running current out when VGS is smaller than the threshold voltage. The thing is that the current that the transistor is conducting is so small that you just despise it, neglect it. It's not important. But still, this decreases exponentially, and it still exists. And this region is usually called the subthreshold region, defined for VGS inferior to the threshold voltage. In this region, for saturation, you have that GM over ID is equal to 1 dividing by an n factor times the thermal voltage. For pointer is around 28 volts minus 1, and here you've got the thermal voltage defined. These are all constants. Here, this factor n is here defined with CD, the depletion capacitance. Now, let me give you more or less an explanation of how you're going to check on the transistor parameters. You just put the transistor, you put the voltage source, you're defining the VGS, you put a voltage source defining the VDS, and you just sweep. Sweep, and you check the parameters that you want about the transistor. Now, if you sweep the GM over ID as a function of VGS, what are you expecting to achieve? If the behavior of saturation region was ideal, you would achieve the red curve. You would go here down, and it would start going up a lot until you hit the threshold voltage. As per the subthreshold region, you would have a constant 28 GM over ID value. But if you grab a transistor and you put it in the lab and you test it, your GM over ID is going to be like the red curve. The behavior is going to be more or less like this. Also, it's usually defined, there are 3 regions defined for the transistor regarding the VGS. You've got the strong inversion for when the VGS is much higher than the threshold voltage. You've got the weak inversion for when it's much lower than the threshold voltage, and the VGS and the moderate inversion when it's approximately equal to the threshold voltage. Now, when using this, when you're sizing your transistors, defining your operating points and checking how does it behave, you plot your transistor parameters versus GM over ID. You can plot parameters as the current, the gain given by GM over GD, the output resistance, the gate capacitance, the transition frequency to check the speed of the transistor, the normalized current to check different transistors, and whatever you find important to use. So now on to the suggestions from my perspective, from what I've done. Plot the transistors in the x-axis and the GM over ID in the y-axis. I think it's better for reading the behavior of the parameters. Then plot each current for different VDS values in one graph. You can also plot for different lengths, different width, just to check how does the circuit behave for different values. But usually if you're designing, well, as I already more or less understand the behavior of the width and length on these parameters, I just go for different VDS values. So this is more or less what it should look like. So you plot for different VDS values, then you've got multiple curves here. You come here, you select, okay, I want to have this output resistance. Come here, I want to have 0.35 VDS voltage. You check, okay, I'm on this GM over ID point. You go on to the other plots that you have. You check, okay, I have this GM over ID. Let me check, for instance, the current, the gain, and so on. And you check all the parameters and the operating point at which that transistor will be on. Last but not least, when designing transistors, start from the hardest. Start from the specs that are turning you crazy, that you want to achieve, that are the hardest, and then go and work towards the easiest ones. So for instance, here this is a very, very simple circuit. I've got here 2 stages. Can anyone here tell me which 2 stages are these? So yeah, you've got here common source and here source follower. So the thing is, imagine that you want to achieve a very high gain with this circuit. First thing you do if you want to achieve a very high gain is you dispose the circuit and you use a better one. But I just want to make a point here that this transistor is it's the one that is going to give the gain to the overall circuit. This one is the one that gives the gain. So if you are given a very tight gain or very specific gain for this circuit, you first start from here and then you work outside onto the other transistors using this methodology. So for now, I'd just like to do a small break, have some water, respond to any of your questions for now. So does anyone have any questions?
Since you're working in industry, when you're in university, you're only working with theoretical numbers and in a perfect state. What is usually the percentage of loss that you're acceptable, that is acceptable for you in your work?
I'm not sure I understand your question. What you mean is in terms of what I lose from university to practice when I go to industry.
Within the numbers. So when you're using the theoretical formulas and you have when you're working with real materials and real transistors, you're bound to have a certain specific block, a certain loss in the capabilities that it has. Do you have a general number of how much that is?
Unfortunately, I can tell you how much you lose from going from end estimation to the actual circuit design. This is mainly because it depends on the technology that you're working. Imagine that you're working with very advanced nodes. Then the behavior of the transistors is so complex that you going by end estimation will give you all transistors outside of what you're expecting. You may even want to have a transistor in saturation, but what you'll have is a transistor in linear because the models are so off. As per the more mature technologies, you have and older technologies. They don't have these kind of effects, so they don't very much, and they are more reliable to use end calculations. Yes. Does anyone here have any further questions?
Eu não percebi bem a ideia do channel, porque o channel estava a passar tipo por cima, mas não devia tipo source ou drain. Será que eu percebi mal?
So let me go back. So you are trying to understand the channel, right? For instance, here. So the transistor is an NPN transistor, right? This means that it needs to have an N part, a P part, and an N part, right? So here the source is the N. On the inside the channel is the P, and here the drain is the N. I'm not sure this answers your question. If this is the...
Aí do gráfico, você tem o source, drain, não é preciso ser o meu canal, porque o meu canal é assim.
No,
Source drain?
this is the gate.
Okay.
So
Ok, isso é... Ok.
this is the gate. So the gate acts on the insulator. The insulator separates the drain from the channel, the gate from the channel, and yeah, this is the channel. This is the P part.
Ok.
Not sure. Does this answer your question? Okay. Anyway. So I would suggest now. Does anyone have any further questions? Okay. Yeah. No.
Eu só dizer que agradecia, também deste feito, sistemas integrados tecnológicos.
Yes.
Fazer o APAM, tal e bom. E também, tipo, começámos a fazer as estimativas à mão e aquilo bate tudo fora, há coisas que deviam estar saturadas no anterior e vice-versa. E como é que tu chegaste à ideia do GM sobre ID? Foi coisa que te deram?
Okay. So.
Porquê?
So
Qual é que foi a motivação? O que é que tu viste nessa abordagem inicialmente que te levou mais por aí, não é?
Okay. So. If I understand your question correctly, you're asking me why I started using GM over ID instead of regular end calculations, and where does this come from? So I've learned this when I was abroad in Erasmus in another university, and the method came. I thought that the method was quite interesting, and it could have benefits for design, and I believe that it gives a better starting point. If you do see it again, you'll notice that you check the transistor parameters, you define the operating points, you assemble everything together, and it will all come together very, very good, very, very well. This is something that I've noticed using GM over ID methodology, and that's why I'm here to teach you. It's something new. I don't believe it's taught at this university. Well, I've studied here, and yeah, just wanted to give you a new view or new idea for the future, and even for when you when you enter this industry.
Mas, por exemplo, com muitos transistores, isso já começa a ser um bocadinho pesado usar isso, ou não?
No.
Ou até mesmo circuitos médios, claro, que ainda consegues usar?
Yes, you can.
Eu li uns quantos papers em que já vi pessoal a desenvolver circuitos mais do ponto de vista como se fosse devido aos modelos sendo complexos, como se fosse um problema de optimização. Então, tipo, já dá para utilizar os modelos todos, porque não para fazer à mão, não é?
Yes.
Torna-se complicado formular o problema.
Yes, when you automate design, it usually uses it usually uses also graphical methods. The thing is that you need to write the code of the optimization by yourself. That's the hardest part. This one you can do it by hand. The GM over ID, you look onto the graphs and you select, okay, I want this transistor to be in this point. And you define it and it's done. Then you assemble everything together. For instance, the circuit that I've developed, like I told you, 20 to 30 nodes. I think that's already complex enough. So I'll now be advancing on to the second half of the presentation. Like I told you, we'll start with the advantages comparatively to the pointer bulk technology. But first, let's revisit both transistors. So what are the main differences between this and this? The main difference is that the gate in the FinFET covers more surfaces than here. Here, the gate covers just one surface, and while here the gate covers 3 surfaces of the channel of the transistor. Also, this transistor, the FinFET, starts being more of a 3D transistor because it uses also not only length and width but also height. Well, here you don't use the height for anything. So let's revisit two things that I've already told you, were the issues from the planar bulk transistor. One is the leakage. Like I told you, it flows through the substrate. While here, the gate surrounds most of the channel, so the leakage that passes through here down here, it's not much. Also, the Dibble effect is much smaller because you have better gate control. The gate, like I told you, it's all around the channel, and it doesn't allow the drain to get that deep inside the channel and reduces the Dibble effect. So you got a stable, more stable threshold voltage. One consequence is the smaller body effect. This easy to see. Here you have the body. Well, the body here, you define the voltage of the body, and it enters directly here into the channel. You've got the full channel here. Got all the surfaces. Well, here you define here for the body. You define the voltage. What happens? You possibly affect here the beginning, but you don't affect the entire channel upstairs. So this can be seen as an advantage for people who are trying to achieve linearity in amplifiers, for instance. You have a cascade, and the body effect usually doesn't help. So this can, for FinFETs, as you don't have body effect, it helps. As for, it can also be seen as a disadvantage for those who are trying to achieve calibration through body effect. Another advantage that you have is higher device density. This comes, I believe, also easy to see. This transistor is a 3D transistor. Imagine that you grab, you unfold the transistor into a planar. What does this mean? This is the width, right? And now imagine that you unfold it and put it down like this, and you unfold this 3-fin transistor. You are going to get a transistor which is much wider than the one that you're seeing here. So it has higher device density. Also, it has higher intrinsic gain. This due to the reduced Dibble effect. The Dibble degrades the GDS a lot. And for the FinFET, as it doesn't have much, the GDS is quite smaller, and you get a higher intrinsic gain on this transistor. Also, it doesn't have any, the pollution capacitance is reduced. You have a higher GM over ID. It's also faster in digital terms, and it has a better gate matching due to the fact that the channel is undoped. The technologies, the channel is so small that you end up having one atom of impurity there. So it's highly and it's undoped, and as such it has better gate matching. So this is easier to scale. Well, it's the transistor, the technology that has been scaled the most. It exists in 7 nanometer. 5 nanometers is coming soon. And I wanted to speak to you a little bit about the ideal digital scaling theory. So the idea that started everything here. So when you scale transistors, you scale horizontal and vertical dimensions by alpha. You reduce the threshold voltage and supply voltage by a factor, and you increase all doping levels by alpha. What does this cause? First of all, you reduce the current used in the circuit by a factor of alpha. The capacitances are also scaled by alpha. When you calculate the delay on an inverter, you get also a factor of alpha, and also the power scales. Now, be careful with this formula, because there is something missing here. When you're trying to scale the power, you're also scaling the dimensions. So you want the power for the same dimensions. So actually, the power when you're scaling it decreases only by alpha for the same area. Now that I've spoken about the advantages.
Per device, for the area is 1 over alpha, but for each device is 1 over alpha cubed.
Sorry, you mean here the current?
It scales as 1 over alpha if you look at 1 square millimeter. So it's no, what?
Yeah, for a scale device, it scales by 1.
The power.
Yes.
But in the same area, you have more devices.
Yes, exactly. You have more devices. You scale by alpha, you have more devices. That's why you need
Per
to
device,
multiply.
For each device, it goes down as 1 over alpha.
Yeah, to the cube. Yes, that's per device. So I'd like to invite the audience to tell me which. So what do you think are the applications of the FinFET? What do you think they are used for? Can anyone try and have a guess?
Medical applications.
Medical applications. Actually, I'm not entirely sure it's used for medical applications. Actually, it has very large-scale applications, but there's other kind of applications. First of all, looking into the advantages of this circuit, this is perfect for processing circuits because it's fast, it's small, it increases it's perfect for processing circuits. So it's used mainly in computers. Your computers at home have FinFETs, possibly. It's also used for wearables. It's used in data centers, supercomputers, AI and deep learning because they require a high processing power. Also, it's used for networking because as small transistors, they have a lot of speed. And it's used in networking, which is the field which I work on. And you have it on 5G and also on it's also used on the physical layer of the internet. Now, on to the challenges. So, working with FinFET is not easy. It also has its limitations. Although I've shown you that the current goes down, when you're working with industry, what do the clients want? So, if the power goes down, and the current goes down, I want the specs to be better. So they start asking more and more, and you end up having high current density. So this high current density causes two main issues to the transistors. One of them is self-heating, which is caused by power dissipation on the channel, and also by poor thermal conductivity. So if you remember, the transistor has an insulator, and you got all the activity occurring inside the channel. But the thing is that in planar transistors, the heat is all dissipated through the substrate, while here it doesn't have anywhere to go, so it remains here. This is one of the major issues of FinFET. Now, here comes the second one in concrete, which is electromigration. These two working together are very strong. So, first of all, what is electromigration? Whoops. So, when you have a real circuit, it's not just the transistors. You need metal lines to connect all the transistors, and you have multiple layers of metals. And here you have a metal. Throughout time, and you have currents flowing through the metal back and forth. But from time to time, you have an electron that comes with such a strength, it's an atom, and dislodges the atom from its place. And it can cause either voids or helix. And this is more or less what it looks like. So if you're wondering what happens when circuits become old, why your phone is not working, it can be from the software, it can be from this. If it warms up, it most likely is from this. So this can cause failure in circuits. You can get this completely open, an open circuit here. And electromigration is checked. It's a reliability measure. It's used for check the aging. So this formula here, it's an empirical formula, and it calculates the mean time to failure. Now, the part that I want you to have attention here is this one. The mean time to failure caused by electromigration is proportional to the exponential of the inverse of the temperature. What does this mean? Temperature goes up, the mean time to failure goes down exponentially. Now, join these with self-heating, and you start having issues. Another challenge of FinFET is high metal resistance. So here we've got a piece of metal that is used in circuits. Can anyone here tell me what is the formula for the resistance of this piece of metal? Come on, anyone? Electromagnetics and optics. Have you forgot it? So the formula, it's the resistivity times the length dividing by the width and the height of the metal. But scaling increases the resistance of the metals, of the metal lines. So this causes challenges like the IR drops, because your circuit, like I told you, it has multiple metal lines to connect between all the transistors there. And when you supply a circuit, imagine a cake with multiple layers, and on the top is where you put your supply, and the supply needs to go down, 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 down to the transistors which are at the bottom. It needs to go through all the layers. And here you've got an amplifier. Imagine, and these are the supplies. Imagine that you have here 200 ohms parasitic resistance, 200 ohms here, and that this uses 1 milliamp current. You're losing here 0.2 volts. You're losing here 0.2 volts as well. This degrades the performance of circuits. This is also seen, for instance, in R2R DECs. You've got a parasitic resistance between this point and this point, this point and this point, also after the switches, between the switches and the resistors, and this can become a problem if you don't tackle it. Also, when connecting two transistors, like I told you, you have a metal line, and this metal line can be seen as an RC structure. So you've got here a resistor. You can imagine the model of this metal line as a resistor, then a capacitance, then a resistor, and there's a capacitance. And this is what is usually called metal line RC. So you want faster circuits, right? But you're decreasing the size of the circuits. Although the capacitances, I prefer not to speak about them because the way that they scale is very complex. The resistance goes up. So this does not help with the increasing the speed of circuits. Also, you'll notice that vias can go above 20 to 50 ohms in FinFET nodes, and that metals can go above 0.5 to 1.5 ohms per square. So for those of you who are not, who haven't heard about squares in metals, so you can imagine it's like having a width and a length, a square of equal length and width. So for instance, this metal line would have like 1, 2, 3, 4, 5 squares, more or less, just to give you a rough idea. FinFET itself is a quite complex structure. It presents, it's very hard to attain for all the parasitic capacitances, for everything. And let's look onto design. In this case, well, as the parasitics are complex, it's hard to integrate that into your models. And when you extract your simulations and you go and test them and verify them, you'll notice that they take a long, long time. Even longer than what is used for usual for previous nodes. Also, in terms of layout, you have a large amount of rules. For those who do layouts, these spooky. Because it has increased exponentially the amount of rules used in layout. you have design rule manuals that can go up to thousands of pages. Imagine doing that layout with that amount of rules. You also have multiple masks per layer. So designing, for instance, for metal 1 or metal 2, you need to use multiple masks. And the projects, doing a project in this is quite heavy. So a mask can cost above $50K to $200K. Development of a single project can cost hundreds of millions. Hundreds. That's a big number. And a single project can take some years. 3 years, 5 years, something like that. So let me speak to you a little bit more about layout. What, if you're working in a technology like this, what you would expect to find. First of all, when you're placing the transistors down, you have a fin boundary, and you need to follow that fin boundary. So, like I told you, yes, you've got here the fins, and when you're imagine placing a 2-fin transistor down, the way it looks like is more or less like this. Wait, sorry. You're trying to put it down, but you can't put it in between the fins because they are defined, and you need to follow the fins that are placed down. Also, besides this, you've got multi-patterning. So these to be able to have metal lines which are closer to each other. If the foundry was trying to do these metal lines with only one layer, what would happen would be quantum effects, where this could merge, or there could be a hole, an open circuit somewhere. So instead, what the foundry does to make the metal lines closer is just to have 2 masks, one red and one blue, and this way you can place the metal lines closer to each other. Also, you have cut metal layers. For instance, in this case, if you have a cut metal layer here, you're separating this part from this part, this part from this part, and etc. But the thing is, if you were trying to do this in the foundry, in order to respect the design rule manuals, in order for you to not have any issue, these two would need to be further away to be safe. Instead, cut metal layers are used for them to be closer. So now on to the potential future of solid-state circuits. I want to speak to you about the potential transistors that are coming. These are nanowire FET, complementary FET, vertical FET, and stacked FETs. This is the expected evolution. Then I've also like to present you something new, not much related to transistors, but also related to the topic, embedded non-volatile memory, namely spin transfer torque magnetic run, which is something that it's being developed by foundries and is expected to have production in 2018, 2019, 2020, and I wanted to expose you and to share this with you. So, first of all, let's look at the FinFET again. So this is the way it looks like. Got source here, drain here, gate, etc. The evolution now is to transform this into a gate all around. So here the gate is on 3 sides of the channel. Next, we're advancing onto a gate which is all around the channel, and we're starting to accumulate transistors in vertical. So these are the nanowires. So the idea is to be able to stack the nanowires as much as they can on a single gate. This will increase the width of the transistor. So the next step is to go on to having PMOS and NMOS in a 3D setting. So you can just have the PMOS up, the NMOS down, and you can just short here and use the transistor in a 3D sense and try to take the best out of it. After this, the second part is to make the nanowires vertical. This will allow for better 3D structures to be built. The idea is to actually stack the transistors, stack gates in horizontal planes, and increase width. Start having the transistors in a more 3D way in order for you to follow Moore's law and achieve more transistors in one single chip. That's the main idea. Now on to spin transfer torque. So this idea is based on quantum mechanics and uses spin polarized electrons. So electrons have an intrinsic property called spin, and this spin is either up or down, just to simplify it. When you pass the electrons through a ferromagnet with a certain magnetization, what you get is this. They all align with the magnetization of the ferromagnet. This effect is used in a magnetic tunnel junction, which is this that you see here. You've got two ferromagnets separated by an insulator, very small insulator, and they have a free layer and a fixed layer. So how does this work? So the free layer can change its magnetization, but the ferromagnet is fixed on one direction only for the magnetization. It never changes throughout the lifetime of the circuit. So the way you read in this memory cell is depending on the magnet's polarization. So imagine that the polarizations are aligned. So this one is pointing up, this one is pointing up. Then you have a small resistance when you try to pass a current through this. If they are anti-aligned, you try to pass a current through this, it will show a high resistance. This is usually written using spin polarized currents or other options, but the most common one is spin polarized currents. And this is very attractive due to the fact that it uses one transistor only for the memory cell. So this that you're seeing here is one memory cell. And when you stack them up in a RAM, it looks more or less like this. So it's quite simple. Now, let's look why this is so attractive, why the main reasons why. So let's look onto the characteristics. First, it's non-volatile. You turn off the circuit and the memory is still there. Also, this is highly scalable, below 10 nanometers. You start making these smaller and smaller, and the amount of current that you need to change the magnetization on the free layer, it's each time less and less, so you consume less and less power. Also, this is high performance, it's low power, and it's low cost. But the fact that actually shows that this is quite attractive is the fact that you have foundries starting production of this in the next years, and also this one. So I've reached the end of my presentation. I would like to acknowledge FCT, Técnico, IEEE, IEEE CAS, IEEE SSSC, and Socionext for helping me on with this presentation. I would like also to acknowledge and to thank Professor Jorge Fernandes. He was my master thesis supervisor. He was a great teacher and had a good influence on me. I would also like to thank Professor Luís Oliveira from FCT Nova. It was him who helped me prepare the seminar for FCT, which I'm presenting tomorrow. Also Professor Marcelino Santos for also helping preparing this seminar, and Professor João Oliveira and Professor João Góes from FCT Nova. Last but not least, I would like to thank my Socionext colleagues, which gave me a lot of feedback on my presentation. And most important than the finish is your support. Thank you for being here, and thank you for being an awesome audience. Thank you.
I think we can all open still the talk for the session for the investors that have recently.
Yeah.
Do you have any idea on the actual fabrication process on the FinFET? How the rare earth depositors as to do the distributed structure? Do you have any idea of that? If it's really high in terms of
Well, regarding the question regarding the process of building the FinFET, so unfortunately, I haven't looked much into detail on that part, as I work mainly on design. So fortunately, I'm not able to give you much about the process of how it's done, the etching, how everything is done. I'm sorry, but thank you for your question. And
probably
yes, yeah.
Estamos a desenhar, faço o circuito, não é? Fiz uma determinada topologia e, digamos, faço o circuito sem amostra normal. Depois vou e tento fazer um FinFET. E há uma altura em que tens de ver qual é a sensibilidade dos meus specs face a parâmetros de construção. Faço um carro, na prática, quando tu fazes, por a tua experiência, tu notas que a FinFET é mais sensível ou é menos sensível, portanto, quando fazes um Monte Carlo.
Ok.
Quanto é que, às tantas, também não é necessário começar a evoluir mesmo as próprias topologias que nós utilizamos. As topologias que nós fazemos, por exemplo, switches, etc., não é melhor começar a arranjar outras maneiras de construir de modo a diminuir a sensibilidade desses parâmetros.
Okay, so if I understand your question correctly, you're asking about design oriented to Monte Carlo worst cases or issues. Yes. So the thing is, first of all, regarding like I've pointed out before, the one of the advantages of FinFETs is that you have better gate matching. You can see here this. You have a better gate matching. You have a smaller AVT here. So first of all, using FinFETs instead of planar transistors, it's per se it's already it already improves the Monte Carlo variations. But when you usually design circuits, you're always trying to have the Monte Carlo issue in mind. There is not exactly a Monte Carlo oriented flow or design flow. Actually, when you do your design, you have to account for that. You first design trying to achieve your specs, then you check if with corners variation, with Monte Carlo variation, process mismatch, how does that affect your circuit. And it's, yes, there are circuits which are more prone to Monte Carlo variations. But in digital terms, mostly there's not much you can do. What is seen and used today as digital circuits is it's mostly developed, and structures that are used nowadays are the ones which present the best, or most often are the ones that present the best characteristics. Yeah, best performance. I hope this answers your question.
Any other questions?
Because of the stacking the transistors vertically, do you need to have any special cares when designing the circuit? For example, I remember from the microelectronics classes. For example, if you put metal wires above a capacitor, there may be
They're coupling. There's coupling.
Yeah, it can affect the circuit in a way you don't want it to. So when you put the transistors vertically, does the way to design the circuits change a lot, or you can just basically put any wires you want? Okay.
Yeah, actually, layout and design, at least for advanced nodes, I would say that they come very hand in hand, because you need to think also on the way that you're going to lay out in order to achieve the least amount of parasitic capacitances to the most balanced circuits. One rule of thumb is to do the layout as symmetric as possible. I understand your question, but you don't only see these, for instance, on stacked transistors. The FinFET itself has already very complex parasitics. Let me just give you a simple example for you to think about it, because the parasitics are all related to the layout itself, so the way that the transistor comes physically, how it looks like. So for instance, here, what are the parasitics that you see here? You see parasitics from the source here to the gate, from this source to the other source, from the source to the gate, from this metal here to the gate. You have very high and very not very high, but very complex parasitics here. When you go down to the other nodes, to the nanowires, you're going to have parasitics even more complex. But that's problem for the process engineers, not for the design engineers, because we just receive the models and we try to do the best we can with the models we're given. I hope this answers your question.
Yeah. Also, what you use cadence or some program like that to design, right?
Yes.
Because the structure is not three-dimensional. I mean, what exactly is a layer? So when I had microelectronics, a layer was a whole plane, right?
Yes.
So how does it? What is exactly the definition of layer in topology?
So you can imagine the layer the same way as okay, like this. This is one layer. This metal one. You can forget here these squares, which are the vias, supposed to be the vias. But for instance, this is supposed to be one layer and one layer only. But you use multiple masks. You use here this to you use one red mask. You use one blue mask. Also for the cut metal layers, you have one cut metal layer for the red. You have another cut metal layer for the blue. So this all itself is one layer, because in the end, what the circuit, what the layer itself would look like is something like this. You would have here a rectangle, here another rectangle, and here these parts, here this part. So this is what the layer itself would look like in the end.
Any more questions?
Ah.
In the advantages, you say that the GM, the intrinsic cadence is higher.
Yeah, the higher GM over ID.
So this means that analog designers are coming back, working this technology, or is it still designs?
That's a tricky question, because analog designers care mostly about gain, and gain comes from the length. So yes, there's room for analog design. It's harder to achieve because due to the size limitations. Also, for instance, you have to do, if you're trying to have high currents, if you're trying to drive high currents onto a load, you need to stack 10,000 transistors or something like that to achieve almost 2 amps, almost 1 amp or 2 amps. And for it to be able to support the electromigration issues, it has its challenges, but there is room for the analog designers. But there's also one con on the FinFET, which is for the same overdrive voltage, you'll notice that the transition frequency is smaller for FinFETs than for planar. But at least the FinFET doesn't have leakage. I hope this answers your question. Thank you.
I also have a question. Well, I don't know if you can answer it. The circuits you are designing are mostly analog, digital, or mixed signals?
Mixed signal circuits.
What is the percentage of digital?
So what I work the products of my company, they developed so they do the conversion from optical signal onto electrical signal. So they need a lot of they have the ADCs and the DACs, of course, which are the mixed signal, and then they have a digital part, mainly digital part. So it's mostly digital. You won't find people using analog, these with analog, as first of all, it's very expensive. Like I told you, and like I told there, hundreds of millions.
Because it's much has a much lower cost.
Yeah.
You can also have better performance.
Yes.
So I would identify computers that they listen to supercomputers, FPGAs, and so on for FinFET. Most of the other DC circuits.
Well, the thing is that the FinFET is the faster technology in the market. So this is the reason why FinFET is mostly used. Yeah, for end applications. Yes.
Okay. Any more questions? So I will ask you to consolidate.
Thank you all for coming. I hope you enjoyed the presentation.